Hello everyone, welcome to lecture 19 on finite element method. As I mentioned before, today we want to move towards two-dimensional finite element method. Before that, I would like to quickly go through what we have done. And let's say, again, we review the roadmap that we had, and we have seen this so many times together. So if you look at this roadmap, the starting point, again, is the strong form, which is a differential equation usually. And then you go from strong form to weak form. Then you have the approximation. You use, let's say, shape functions for approximations, but also you use them for transformation from physical space to natural space. And you also have numerical integration using Gauss quadrature. And then eventually you will have your stiffness that you assemble elements together, and then you can solve it, and that would be the solution to your problem. As I mentioned before, this roadmap is valid for one-dimensional FEM as well as two-dimensional FEM, as well as three-dimensional FEM, but we are not talking about three-dimensional finite element method here, but the roadmap stays exactly the same. So what we want to do is basically going through these stations again, or these milestones together in a two-dimensional setting. Again, this slide, the basics of the finite element method and the sources of the errors are exactly the same thing as we discussed before. But now even when we wanted to discuss about this before, we talked about this two-dimensional mesh anyway. And also this, let's say, this second realization of the roadmap is also true, except that here, for instance, specifically, we wrote these one-dimensional equations. Now, these one-dimensional equations, they would transform to their two-dimensional counterparts. So based on that, we had this short overview of one-dimensional FEM. So we said basically the starting point is a differential equation, second order differential equation. You multiply by test function. Okay, test function is displacement variation or virtual displacement if you want. So you multiply by the test function, you integrate it. After that, you just reorder the terms, you identify the forces, and then you put all these equations together, and using the arbitrariness of those test functions, W's, you end up with this form which looks like a matrix times displacement equals forces. So this reminds you of your, let's say, Ku equals F, and that would be exactly your stiffness matrix. Now, each component of the stiffness matrix is calculated like this. And the next thing, or the last thing we had to do, was to transform these into, let's say, from physical space into natural coordinates to integrate them numerically. That was the last thing we did. And once you do that, we are done. So basically, this slide is sort of everything. You deal with some sort of a stiffness matrix, and each component of that is calculated like this. In this calculation, you are dealing with the physical space. So it's dx. This is integration over L, and the primes are the derivatives with respect to x. Whereas you need to transform that into natural coordinates, and then in the natural coordinate system, you can integrate it like that, and that would transform to a summation over the Gauss points, basically. Now, it turns out if you had a two-dimensional finite element method, formally you would have the same thing. I cannot jump to that now. We need to basically go through the mathematical steps and derivations for that. But what you will have eventually is, again, some sort of a stiffness matrix with its components being related to the derivatives of shape functions, but now shape functions would be in 2D. And then integral of that over the physical space. And also what we do in 2D is also the same. We transform the physical space into natural space, and then we use Gauss quadrature for that. Okay, so we want to do that. That's the essence of the, let's say, two-dimensional finite element method. And as I mentioned, this would be sort of the starting point also from now on, because again, the roadmap that you see here has not changed. It's exactly the same thing. But before I can talk about that, we need to talk a little bit about, let's say, mathematical preliminaries. These are the steps, or let's say the equations or the information you need to proceed with two-dimensional finite element analysis. The first component of these, let's say, mathematical preliminaries is the Einstein summation convention. We talked about this before. So Einstein summation convention basically tells you that if you write your vectors or matrices in indices, so instead of saying that I have a vector v, usually you would say it is vx, ex plus, I don't know, vy, ey plus vz, ez. So instead of that, if you just write it in terms of its components, so v1, v2, v3, now 1 and 2 and 3, they correspond to x and y and z direction. Okay, so this is the idea. Instead of using x, y, and z coordinates, and by the way, if it is 2D, usually it's only x and y anyway. But instead of using coordinates numbering, we want to, or instead of using coordinates names like x, y, z, we will call them 1, 2, 3. That is just as simple as that. Okay, so again, this property basically tells you, well, if you have a dot product u dot v, I mean, usually you would say a dot product u dot v is, I don't know, ux vx plus uy vy plus uz vz. But now in this case, it would be simply u1 v1 plus u2 v2 plus u3 v3. And because it looks like that, then it's exactly a summation over those. And also we said, if you have a summation and then you have a repeated index twice, you don't need to write that summation. So this is how you can write that thing. So instead of u dot v, you can write something like ui vi. So why is this interesting? Because also, for instance, instead of multiplying two matrices together, let's say you have a matrix A and you have a matrix B, and imagine they are, I don't know, 3 by 3 matrices. I don't want to write them in components and take your time, but imagine these are just usual 3 by 3 matrices in 3-dimensional space, and you know how to do matrix multiplication. So basically, if you want to do that, you can write it as this, that A, I, J, B, J, K is C, I, K. Okay, so basically it tells you that if you choose a specific I and K, okay, so let's say for instance, if you assume I equals, I don't know, 1 and K equals 2, then A1J, BJ2, this would be your C12. And you can obviously see that there is a summation over J because J is repeated twice. So this component would be A11, B12 plus A12, B22 plus A13, B32. Okay, and as I mentioned, essentially, if this is your matrix A and it has 3 components in each direction, and this is matrix B, So if you want first row, second column of the multiplied matrix, this would be basically first row of A times second column of B, right? That's how you multiply it. So that would be exactly what we have written here. So A11 times B12, then this one, A12 times B22, then this last one, A13 times B32. Okay, so this thing, this technique, basically, it allows us to write these usually long expressions in a much more elegant manner. And obviously, the reason I'm spending time on it, and I tell you, is not because we just want to do matrix multiplication. We will have a better use for them soon. So that's why we need to learn this. Okay, so that's the first thing. Now, remember, we have this sort of dot product. So what does the dot product do for you? You get two vectors, and it gives you a scalar value. Okay, so this dot product, it does this thing, dot product. Think of it as an operator, as a function that it takes two vectors. It takes vectors u and vectors v, and the output is a scalar value. And how does that scalar value works? That scalar value gives you one-to-one multiplications of each component or of the components, and then summation over them, right? So this is u1 v1, u2 v2, u3 v3. Okay, so maybe if we want to, we can also define some sort of dot product between two matrices. By the way, I'm calling them matrices. They are tensors, but for now, let's just call them matrices. I think it's easier. So let's say you have a dot product of two matrices, A and B. And we want to define something which also gives you a scalar value. And we want it to follow exactly what we did before. So in the previous case, this thing was ui vi. If you have a dot product between two second order tensors or two matrices, in this case, let's just call it for simplicity, you can write it as aij bij. All right, so now you have two loops, and basically if you wanted to expand this, this would give you something like a11 b11 plus a12 b12 plus, you keep going until the end, right? So a23 b23, and sorry, 32 32 b32 plus a33 b33. Okay, so you just have a summation over pairwise multiplication of components of both matrices, and we call this also a dot product. So it is essentially a dot product because it takes two inputs and it gives you a scalar value. But in order to sort of distinguish that for ourselves, we can also call this a double dot product. Okay, so why do we call this a double dot product? Because that is going to be the way that we are writing it. So remember here, this dot product is just u dot v, so it is one dot. Here you can write this a, two dots, and then b. Okay, so we write this double dot product like that for for simplicity, to distinguish between the two. It's a nice definition, and it comes handy later for us. Okay, so if you have two vectors, now we have learned that you can define a product like this, but also I want to define a different type of product between two vectors. So again, let's see what it does. This product, if you have two vectors, it gives you a scalar as output. Now what we want to do is to define a product that you throw in two vectors, and then you get a matrix or a tensor as output. That's what we want to do. Just give me a second. All right, I think it's better now. So what we want to do is to define a different type of product between two vectors, and something that will give you a matrix or a tensor in return, and that we call the Diodic product. Okay, so there is this other thing which looks like a circle with a cross inside, and you call this a Diodic product, or simply a dyad. Now, what is the output of a dyadic product? It's something that if you take the dyadic product of two vectors, you get a second order tensor, but let's say in our case, we can call it matrix. All right. And by the way, here the order doesn't matter if you had a dot product, but if you have a dyadic product, the order also matters. And we show this as UIVJ. So see now, you have two indices, I and J, but they are not repeated. So both of them are free indices basically, and that means you have a matrix. So in 3D, you have a 3 by 3 matrix. And we are going to call this thing U dyadic V. So it looks like that. And if you want to show it, it's going to look like this. You have a, let's say, 3 by 3 matrix. And again, if you think about this, for this matrix, the component ij looks like uivj. So if you want to draw it, the first component of that matrix would be u1 v1. The second component is u1 v2, u1 v3, u2 v1, u2 v2, u2 v3, u3 v1, u3 v2, u3 v3. Okay, so this is U dyadic V. And you can imagine, for instance, if you play the same game on, I don't know, on one of these base vectors. Okay, so let's think about a base vector E1, dyadic E2, for instance. E2 is the base vector, is the unit vector in the first direction. E2 is the unit vector in the two direction, or in the y direction. So that would give you something which looks like a 1 here and 0 everywhere else. Okay. So this is something quite nice. And then again, as I mentioned, for now it is just a definition for you, but it will come handy in what we will do through our derivations for 2D. Now, the last thing we want to talk about is this other thing we call Kronecker delta. Let me just put this here. Okay, so there is this other thing we want to talk about and define, and that is Kronecker delta. So you write the letter delta ij. Now, delta ij is essentially ei dot ej. Okay, ei and ej, again, these are the base vectors, the unit vectors of your coordinate system. What does that mean for you? That means if I and j are equal, you get 1. If I and j are not equal, you get 0. And sorry. If I equals j, if I is not equal j. Okay, so you know that property holds between the base vectors, right? So e1 dot e1 is equal e2 dot e2 is equal e3 dot e3. They are 1, but then e1 dot e2 is 0. Okay, so that is another property for you. All right, so let's just put these together. So the first thing is u dot v is ui vi. So we learned this. A dot b. So this is one dot. So it's the usual dot product. It's going to give you a second order tensor or the matrix if you want, and that thing would have a component ik, which would be aij bjk for any I and k between 1 and 3. And then you have u diodic v. And now again, u diodic v is also a second order tensor order matrix here. And it's the component ij of that is ui vj. So we have learned this, and we have also learned delta ij is ei dot ej. Now you can sort of mix and match these. An interesting component, for instance, would be if you think of a dot u. So if you have a matrix times a vector, now that gives you also a vector, and the component I of that would be something like aij uj. Okay, and then again, j is repeated twice, so it's a summation. Now, a very interesting extension of this line of thinking is when you think of higher order, let's say matrices or tensors. And a famous one for you is a fourth order matrix or a fourth order tensor or a fourth order array. By the way, you can also define this in MATLAB. So let's think of E as a fourth order tensor. Again, you can just, for simplicity, think about an array. You don't have to be, let's say, concerned about the term tensor. Now, this means that in 3D, it has 81 components. Okay, remember a vector in 3D has 3 components, a matrix in 3D has 9 components, so 3 by 3. So this is 3 by 3 by 3 by 3, that's 81 components. So this thing, usually you see it as a constitutive tensor in the context of mechanics and is connecting stresses to strains. Okay, so for you, later you would see this thing in a relationship which looks like this. Now, what does this mean? It means you have a fourth order tensor, you have a second order tensor, which is a strain. You also get a second order tensor that is stress. So that is fourth order. That would be second order. And that is also second order. Now, using what we have up there, we can write this in terms of its components. So this is a second order tensor. That means it has 2 components or 2 free indices. Let's call them, I don't know, ij maybe. That would be then E. E has 4 indices, I, J, K, L, which is multiplied by epsilon KL. Okay. Now, see, it's exactly the same sort of story that we had before for a double contraction of two matrices. We define this thing that if you have 2 matrices or 2 second order tensor, the double contraction of them is just the scalar value. So you don't need these brackets. So that would be basically Aij, Bij. And now this is a similar story. If you have a double contraction here or a double dot, you get this pairwise dot between the last 2 components as if this thing itself is just the dyadic of 2 second order matrices. Okay, you just treat it like that basically, and you get that. So this is your summary of mathematical preliminaries, let's say the notation of mathematical preliminaries. Okay, now using this, we want to go to, let's say, the governing equations for a 2-dimensional problem. Now the key message here is that instead of XYZ, let's get used to just 1, 2, 3. Okay, so from now on, if we want to actually use the coordinates XYZ, we would call them X1, X2, and X3. All right, and instead of EX, EY, EZ, so instead of saying EX, we are going to say EY. All right, so that's that. And then this is not too complicated. As you can imagine, it basically tells you that you have, until now, let's say you had this coordinate system XYZ. All you need to do is to imagine that that coordinate system is now written like 1, 2, 3 directions. Okay, or let's say call it X1, X2, X3. Now, I also keep writing everything in 3D. So it's 2D, by the way. You can imagine in a 2-dimensional setting, instead of 3 by 3 by 3 by 3, so instead of 81, in a 2-dimensional setting, you would have 2 by 2 by 2 by 2, which is 16. Okay, so it reduces the dimension of complexity, but I want to keep it generic because also some of you may be interested in 3-dimensional finite element method. And as long as, or as far as the mathematical preliminaries and the operations and the proofs are concerned, everything between 2D and 3D are identical. And let's say when you write it in this index or let's say advanced notation. All right, so that's that. Do you have any question? So in usual 1D FEM, there was this thing that also appeared a lot, and it was derivatives. For instance, remember the first thing that we had, the strong form itself. In the strong form, you had something which looked like u dot, sorry, something that looked like u double prime. Okay, so if you have a one-dimensional problem, the derivatives are familiar. It's just your prime usually, and you know how to handle them. In other words, if you have, let's say, a y that's a function of x, usually the derivative is easy. So that u prime is just, let's say, f prime of x. In this case, that prime also means derivative with respect to x, of course. Okay, I am using this notation like in curly brackets, something. This means just an arbitrary quantity. Okay, so it's just, I read it as something. Okay, so the derivative of something, is just the derivative of that thing with respect to x if it is usual 1D. Now, if you had a vector instead of that, so let's say you have a vector u, and now that u is a function of coordinates x, y, and z, which in your case it would be x1, x2, x3. But I go back and forth between the two notations to remind you what is what. Now, if you want to calculate the derivative of a vector, you have at least two options. It's indeed you have three options, but I'm talking about only two of them here. You have two options. One of them is that you can calculate the gradient of that. Okay, so you can calculate the gradient of that thing. Another option is you can calculate the divergence of that thing. And by the way, you can imagine if it is, let's say, in a usual 3D, you should have three definitions for the derivatives. Let's say it's a 1D, it's a scalar, there is one derivative. But if it is 3D, you may be able to define three derivatives. For the first and last time, I also write the third one just for, let's say, for the sake of completeness, but we never talk about that. But the third one would be curl of that thing. Okay, so if you have a vector, that derivative, which previously was just a simple prime, now it transforms into three different types of derivatives. It could be a gradient, it could be a divergence, it could be a curl. And now, using the notations that we had, you can define these as follows. Let's say gradient of u would be the derivative, or let's just call it gradient of something, which looks like what we have done before. It doesn't matter. So a gradient of u would be the derivative of u with respect to xi. Now that diodic, remember we defined that product diod, that's that. Divergence would be a similar story, except now it comes with a dot product. And you can imagine why there is a third one. And then again, we never use this, but that third one, you can imagine it's going to look like a cross product, right? So remember, we have three types of products. It's either dot or dyad or cross. So you get three different types of derivatives also based on that. But as I mentioned, you don't have to worry about that curl anymore. I am going to drop it from now on. And then also we write this in a more compact format soon, but you have it now for that. Now that was if U is a vector, but what if you had a scalar? So let's say you have F, or it could be the same that, yeah, like before. So let's call it W maybe, as a function of X, Y, and Z. So now in this case, you have three inputs, but one output. But also then again, you can define still the gradient. So you can define gradient of F, and gradient of F in this case would be the derivative of F with respect to xi, ei, okay, which is very similar to what you just had here, right? So my point is you can define a gradient for a vector, you can define divergence for a vector, but if it's a scalar value, you can only define gradient. Now, obviously, the game doesn't end here. You can also extend this to higher orders, and that is kind of the reason we talk about this. So if you think of all of these are sort of the vectorial versions, but you can also think of higher orders and matrices if you want. So let's say now you have a matrix A that is I don't know, a function of also different coordinates, so x, y, z. Also in this case, you can define gradient of A, and also you can define a divergence of A. Okay, but then the idea would be the same. Now, gradient of A would be derivative of A with respect to xi, dyadic ei. Divergence would be derivative with respect to xi dot ei. And then also while we have this, let me put them here. So divergence of a vector is derivative of that vector times xi dot ei. And then here you have the gradient of that vector. All right, so this is everything basically. So this is kind of the compact notation. But what we want to do is to write this in terms of more, let's say, more tangible formats. So think of a scalar valued function phi. Phi of x. Okay, so phi is a scalar value, x is just your vector x. That means phi is a function of x1, x2, x3. which again, in your old notations, that would mean it's a function of x, y, z, if you think of coordinates x, y, z. Now, if I want to define the gradient of phi, as I mentioned, this is derivative of phi with respect to x, I, ei. So here you have this I repeated twice, so you would have a summation over that, which means this is derivative of phi with respect to x1, e1, plus derivative of phi with respect to x2, e2, plus derivative of phi with respect to x3, e3. In other words, if you wanted this in, let's say, in Cartesian coordinates, in usual x, y, z coordinates, it would be derivative of phi with respect to x, dx, plus derivative of phi with respect to, let's say, y, ey, plus derivative of phi with respect to z, ez. And maybe that reminds you now of, let's say, your famous gradient that possibly you used to write like this: derivative of phi with respect to x, derivative of phi with respect to y, and derivative of phi with respect to z. Okay, so gradient of a scalar value is a vector. That vector has three components, and it looks like this. Okay, so again, maybe possibly you have seen this before, or that is the way you used to do it anyway. Okay, let's keep this on the side for now. Okay, so this is the gradient of a scalar valued function. And as I mentioned, for a scalar valued function, you cannot calculate divergence. You cannot calculate curl, because divergence and curl, they require a vector or higher order. But as long as you want the gradient, it looks like this. And it's basically the source of your directional derivative. I also mentioned something very briefly here. So usually, remember the sort of the inverse of derivative or the differential operator. So if you have just the usual function, let's say if you're dealing with the scalars only, think of y equals f of x. So you would have y prime let's say as the derivative of, or maybe let me just call it f prime for simplicity. F prime is the derivative of y with respect to x. Okay, so based on that, you remember, let's say if it is just a complete derivative, you can also write dy equals f prime dx, right? So this gives you something to write that incremental form. Okay, so you have the same story here. If you have the derivative, you can always say the phi, or the change of that scalar function, is that gradient operator, which is a vector now, by the way, dot product dx. But now dx would also be a vector. Okay, so this also works for you, let's say, in that manner. And maybe, for instance, if this thing is 0, it means these two can also be orthogonal to each other, and then it comes to this notion that you would say gradient is orthogonal to the surface of the function or something like that. But this is the first part. The second thing we want to do is to to use this now and to extend this, but we want to go to a vector valued function. So this was all scalar valued. The next thing I want to do is a vector valued function. Maybe we call it U so that it reminds you of displacement, because later the gradient of displacement would relate to strain. So it's not a bad idea to have that. So this is what we want to do. We want to calculate the gradient of U. But let me do it after the break. We are 1 minute gone. Okay, so we continue at 9:30, 9-minute break. All right, so we want to define the gradient of a vector now. And as I mentioned, this vector, itself, it depends on 3 coordinates. So you can imagine it has the first coordinate u1, u2, u3, so 3 coordinates. But then each coordinate is also a function of x1, x2, x3. This is the situation here. And then again, you can use these brackets to remind yourself that this is a, let's say, 3x1 matrix or array, or otherwise you call it a vector. So gradient of this, as we discussed before, would be the derivative of that with respect to, let's say, each component, Diodic EI. That is how we define this thing, right? And then here you can imagine you would express this as a vector like uj, ej, right? So this is basically u1, e1 plus u2, e2 plus u3, e3. So if you just insert that here, you would have something which looks like derivative of uj, ej with respect to xi, ej, sorry, Diodic EI. Now, ej is a constant, it comes out. And what you are left with is something like this, derivative of uj with respect to xi, ej Diodic EI. Now, remember I told you about this ej Diodic EI. This ej Diodic EI is like a placeholder. So, for instance, if you think of E2 Diodic E1, this would look like a matrix which is 0 everywhere except it is 1 here. Okay, so that tells you that that component 2, 1, so in that case, this would be derivative of u2 with respect to x1. That component derivative with respect to derivative of u2 with respect to x1, it goes here because it is multiplied with 1 only there and it's 0 everywhere else. Okay, so if you play this game, basically this expression that is in front of you is a matrix, or again is a second order tensor, and what we want to do is to write that. So gradient of u, remember we said gradient of a scalar valued was a vector here. Now gradient of a vector, on the other hand, is a matrix. And then again, if it is 3D, it's going to be 3 by 3. If it is 2D, it's 2 by 2. But then it's like this. Derivative of u1 with respect to x1, it comes here. Then derivative of u1 with respect to x2. Derivative of u1 with respect to x3. Then you have derivative of u2 with respect to x1. Derivative of u2 with respect to x2. Derivative of u2 with respect to x3. Derivative of u3 with respect to x1. Derivative of u3 with respect to x2, and then derivative of u3 with respect to x3. Okay, so the gradient of that vector is a matrix, or otherwise second order tensor. And as I said, if you think of your old notation, I don't know, this thing would have been for you derivative of uy with respect to x. Okay, so but here we just use the numbers 1, 2, and 3. Okay, now if you have a vector valued function, that would be the gradient operator, but also you can compute the divergence for it. So that's what I want to talk about next. Now, the divergence of that thing, on the other hand, it would be derivative of u with respect to xi dot ei. Previously, it was diode. Now, the game is exactly the same game. It would be derivative of uj ej. Remember, that's how we wrote u with respect to xi. Now, dot ei. And see what happens next. This is derivative of uj with respect to xi. Again, ej comes out. Now, if you look at ej.ei, you remember this is your Kronecker delta. So it's that thing that is 1 only if I and j are equal, and if it is 0 if I and j are not equal. So this whole thing can be written as derivative of ui with respect to xi. And then again, I is repeated twice. So that means there is a summation. Okay, so if I keep the gradient on this corner, we can also write. Can you hear me?
Yes, hocam.
Can you see my screen too?
No, hocam.
No. All right, so I think we are back, hopefully. Okay, that's that. So basically, again, in summary, if you just look at what we had, if it is a scalar field, this is the gradient. I write this sort of, the derivations or how we get there, because I think that's the nice way to see how it got there. But it's not that important for you. For you, important is that if you have a scalar field, that's the gradient. If you have a vector field, this is the gradient, and this is the divergence. Okay. Now, the next step would be, remember we had a scalar, we had vector, and now we go to a higher dimension. So it would be tensor valued function. again, for simplicity, I call it matrix valued because I want to avoid using the term tensor here, but it's a tensor and it's a matrix A. It's a, let's say, 3 by 3 matrix. It's a square matrix and it's a function of X. Again, similar to before. And in this case, we are interested in the divergence operator on A. Divergence operator on A would be, again, similar to what we defined as a unified way of divergence operator. Is simply this dot product, so derivative of A with respect to xi dot ei. Then that would be derivative of A itself. Remember, it can be expressed like this. Now you take ej and ek out because these are constants, so you would have derivative of a jk with respect to x I ej ek dot ei. So that gives you delta ki, or otherwise this gives you derivative of a ji with respect to xi ej. Okay, so now if you look at this, j is the free index. So j is the free index because it is multiplied by, let's say, the base vector. So you have a summation over j. So it's in, well, let's say here it's not a free index. It's still a dummy index because it repeats twice. But you can imagine if I wanted to write the I component of this or the j component of this, it's going to look like this. Divergence of A, the j component of that is the derivative of aji with respect to xi. Okay, now you can see I is repeated twice, so there's a summation over I, but j is free. So what does this mean for you? It means that the divergence of A is a vector. I mean, you can see there is only one of these here. So it's a vector, and like all the other vectors, it has 3 components. And then each of those components, they follow the blue term or the blue format that we have up there. So let me just take this on this corner, and then I'm going to write that for you. So the divergence of A will be again, it's a vector. It's derivative of A11 with respect to x1 plus derivative of A12 with respect to x2 plus the derivative of A13 with respect to x3, right? You can clearly see how this happens, right? It's just basically the summation over I. The second row, so if j is 2, it's going to be derivative of A21 with respect to x1 plus derivative of A22 with respect to x2 plus derivative of A23 with respect to x3. And then eventually you would have the third, so derivative of A31 with respect to x1 plus derivative of A32 with respect to x2. Okay, so this is also the divergence of A. All right, so let's put this all together in a combined format, because we want this, and we will use this in the future. So this is the divergence operator on a matrix. Let's say if you have a vector, this is the gradient, and this is the divergence. So we have most of what we need. So if you have a vector, you know how to calculate the gradient and divergence of that. And if you have a matrix, you know how to calculate the divergence of that. Now, looking at this, you can clearly see what happens with the orders, basically. You see, a vector has the order 1. The gradient of a vector has order 2. So because it's a matrix, it becomes a matrix. Okay, now divergence of a vector is a scalar, so it's order 0. So if you think of, let's say, a scalar to have order 0, a vector to have order 1, and a matrix to have order 2, it seems that gradient increases the order by 1, and divergence reduces the order by 1. So what does that mean? That means the divergence of a matrix is a vector, so it comes from 2 to 1. Divergence of a vector is a scalar, so it comes from 1 to 0. Gradient of a vector is a matrix, so it goes from 1 to 2. I forgot to include the gradient of a scalar field in this picture. Let me also include that. So this is the slide that you will be using, or we will be using quite frequently. I just wanted to be sort of complete. So let me just do it now. So this is the gradient of a vector. And also we had this gradient of a scalar field, right? So gradient of phi. I'm going to also include this into this picture just now. So gradient of phi, it's going to be derivative of phi with respect to xi. All right, so that's derivative of phi with respect to, let's say, x1. Derivative of phi with respect to x2. And well, it's a delicate task here. Okay, now we have it. So that would be eventually great derivative of phi with respect to x3. Okay, so this is all you need to have in one slide, and we will keep using this again and again through throughout the semester. Okay, so do you have any question? Why not? We can put this here. This now looks cleaner. So it's the gradient and then divergence. So why am I talking about this so much? Remember our strong form. Again, it looked like, I don't know, EA, maybe U double prime plus B, and the B was some sort of body force density, and it was 0. So this is in 1D. Okay, so remember this was the strong form in 1D. Now, we want to calculate or we want to compute the strong form in 2D and in 3D. Let's just look at what this thing is a little. If I divide this thing by A, this will look like E U double prime B divided by A. Okay, now B was body force density in 1D. So that was, let's say, force per meter. Does it make sense? So in 1D, your body force density is, so this is a 1D force density. So if you divide it by A, you would have this thing. What would be the dimension of that? It's force divided by meter cubed, right? So it just feels like it's actually the real force density. So this would be your 3D force density. Okay, so in 3D, if you get something like that, you shouldn't be too surprised. Now, what was U double prime? U double prime was, okay, basically U prime prime. And in 1D, U prime is epsilon, right? So this is sort of epsilon prime. Now, you also remember maybe that this was in fact not EAU double prime. I mean, we wrote it EAU double prime because we assumed E and A are constant. Otherwise, it was indeed something which looked like EAU prime prime. You remember that, right? So if now you take that into account and considering that this is EU prime prime, so basically what you have here is E epsilon prime plus B divided by A equals 0. Okay, now let's call this B star for now, or B3D maybe. Let's just call it B3D. This thing is nothing but sigma prime. Okay, so basically what you have, it turns out that your strong form is the derivative of sigma, derivative of stress, plus body force density is 0. It's still 1D, by the way, but I'm trying to give you a different taste of that strong form. So the strong form, which looked like this, it is indeed something like that. So it's sigma prime, it's derivative of stress plus body force density is 0. Okay, now it turns out if we go to 3D, we can mimic that. So again, remember this is just the 1D version of the story for now. It turns out that you can also use stress, but now remember, if you think of 2D and 3D, your stress is no longer a scalar value, it's a matrix or it's a second order tensor. So we need something like this. It would be sigma prime. And then because it is 3D, again, the body force is not just a scalar value, it's also having direction. So maybe it would be just B equals 0. Does that make sense? So this would be now your 3D and 2D, if you want, strong form. And 1D, by the way. So this is just a generic strong form, right? It doesn't know the dimension. So if you look at this, well, 0 in every dimension is 0. So if it is a 3D problem, 0 means it's a vector 0. If it is a 2D problem, 0 means it's, let's say again, a vector of 0. And if it is 1D, it would be just a scalar 0. So 0 is okay. Body force density, again, it's like a vector, it's the same thing. The only thing that is still a little vague here is this prime. What do I mean by prime? Because if you remember, we just said, if you have a, let's say, a second order tensor, you can have two different, or actually 3 different primes. It could be a gradient, divergence, or curve. So which one is it? But then to answer which one is it, which one it is, you can just look at the dimension of what you have here. This is the body force density. A force is a vector. So remember, if the prime here was gradient, then it would increase the order. So you would have order 3 here and order 1 here. This wouldn't work. So the prime there is a divergence. All right. So long story short, this is your balance equation or your governing equation or your strong form in 3D and 2D and 1D. This is the unified strong form. Okay. All right. So let me just start with this now. So the starting point is the strong form for us, obviously, like we did before. And I'm going to just write that. So this is generic form. And as I mentioned, it's simply divergence of stress plus body forces equals 0. Okay, so keep this in mind. Now we want to have a little detour, and we come back to this. momentarily. Okay, so just keep this in mind for now. Remember what it is that we do in, let's say, mechanics. What is the big picture of mechanics? And we have repeated this big picture many times. Then we had our courses ME 231 and 232. So let's say a big picture of mechanics. The goal of anything that we do, and in particular finite element simulations, is to find a relationship between, let's say, deformation and loading, right? So we had this nice picture. If you remember, also many times we repeated this in 231. So there is this big picture basically. On, let's say, on the left hand side you have deformations or loading. On the right hand side, and so this would be something like deformations, and then this would be loading. Okay, so in your case, maybe this loading is usually external forces. And then the question was how you connect these two together. In order to do that, we learned that from deformation, we come down, we come to strain. So let's say deformation is maybe U, the loading is something like F, or force, if it's a mechanical problem. Strain is something like epsilon, and then you would have stress, which would be something like sigma. And then we learn together, or we realize there is no direct connection between the two. The only way to connect loading and deformation is to go through this process. So you need to use basically your definition of strain in terms of gradient of displacement. By the way, this is symmetric gradient of displacement. So that would be the connection between strain and deformation. And then between stress and load, and for instance, if this was sigma and n is the normal to the surface, T would be the traction. So let me just change F to T maybe, so that it reminds you of traction on the surface. Okay, so this thing is basically the so-called Cauchy Theorem. I'm sure you remember that, and we have done this in different forms, of course. And then once you have this relationship between, let's say, once you have the connection of deformation to strain and load to stress, then you had the constitutive law or the material model. So you had this constitutive law, which for us, it was something like sigma equals, I'm going to write it as C epsilon. Okay, now this is again this thing that this is your constitutive tensor, that thing with 81 components, and usually we used as the symmetry property of this, and we used Voigt notation, so you use this 6x6 matrix to identify that. But eventually this is sort of Hooke's law. So you should remember this much, let's say. Well, it turns out that not two, but many problems in mechanics or in physics, they follow exactly the same thing. For us in this course, we want to, in particular, we want to talk about mechanical problems and thermal problems. Okay, so remember one reason that I am teaching this and we are coding this is to show you the significance of the finite element method and what you can do with it. And the idea here is for me to show you that if you have this for a mechanical problem, you can easily also use it for a thermal problem, for diffusion, for conduction. Okay, so, and mathematically, it turns out that the thermal problem is actually simpler than the mechanical problem. So remember this thing. Let's say the left-hand side is the mechanical problem. Now, what we can do is to construct a thermal problem from that. Okay. So this looks like that. If you have a thermal problem, now your unknowns are not deformations, they are not displacement. Your unknowns are temperature. Okay, so this would be temperature. Let's call it, I don't know, theta maybe. Now, your loading is heat flux. And this is going to be a scalar valued heat flux. So I'm just going to call it Q, or maybe I call it Qn for simplicity, or to show that this is the scalar value in the normal direction. Now, instead of strain, you have temperature gradients. Remember, strain is basically deformation gradient, it's displacement gradient, right? Strain is displacement gradient, so you can define this thing as temperature gradient. And this is exactly what it is. So it's the gradient of the temperature, and you can call it maybe, I don't know, letter G. And then you have the heat flux vector, of course, instead of the stress itself. So it's heat flux inside. Q. Now, if you compare with what you have there, the Cauchy theorem here would tell you that Q, so the heat flux inside that vector dot n, this would be Qn. Instead of epsilon equals symmetric gradient of U, you would have G equals gradient of temperature. And your constitutive assumption is very similar to what you had before. It's a connection between G and heat flux. And remember, this is like a linear relationship between a stress and a strain, right? So if you want a linear relationship between heat flux and temperature, then you would have this factor K, you know, which is like a constant coefficient for you times G. So G is temperature gradient. Just historically, there is a minus here because usually you have this thing that if something, I don't know, if something cools down, the heat flux is negative or something. So that is usually like a definition that you have in fluid mechanics or in thermomechanics. So I keep that factor minus for, let's say, notational convenience, but it could be also inside K. Now, K is exactly the conductivity. So K is your conductivity coefficient. Remember, in a mechanical problem, C is your elastic coefficient is the resistance against deformation. In a thermal problem, K is conduction, is the resistance against, let's say, the ability to conduct heat or to diffuse heat, if you want. Now, on the left-hand side, you call that Hooke's law. On the right-hand side, you call this Fourier's law. All right? So this here is a mechanical problem, and this here is a thermal problem. But you can identify these two problems within the same framework easily, right? If you just look at them, you can see how both of them mathematically are, let's say, identical or are formally identical. And once you let's say, once you realize this, then you can use your finite element method for both of these problems. And that's exactly what we want to do. So from now on, we stick to mechanical problems. Also, most of the time we talk about 2D, but everything that we say is also valid for a thermal problem. But not only it is valid for a thermal problem, it is valid at a, at a stronger stand in a way, in a sense that in a thermal problem, G, which is equivalent to a strain in a mechanical problem, it's a vector. So this is a vector. This is a matrix or second order tensor. So basically your mechanical problem is one-dimensional higher in its own space. So here again, stress is second order tensor or a matrix. So a stress is matrix, strain is matrix, and this thing, it has 81 components. Whereas here, this is a vector, this is a vector, and K conduction, it has 9 components. Okay, so that's that. All right, with that, then I come back to this slide, and then remember we said this is the divergence of sigma plus B is 0. If you have a heat flux, then you can also say, well, it's a divergence of Q, now the heat flux, plus, I don't know, let's call it C is 0. Okay. And all you have to do now is to write these, and I'm going to spell this for a mechanical problem and for a thermal problem for you. So for a mechanical problem, this would look like derivative of sigma xx with respect to x plus derivative of sigma xy with respect to y plus derivative of sigma xz with respect to z plus bx is 0. So that's your first equation in the x direction. And then you would have 3 of these. So I'm going to just duplicate and write them like this. All I have to do is to take care of these indices. So the first index is changing only. So this would be now yx, yy, yz. This would be also now zx, and zy, and zz. Okay, so you have these 3 equations, which again, altogether, they just mean it's a divergence of sigma. And as I mentioned, along that way, do not forget that all you do is to write this thing like derivative of sigma with respect to jk, derivative of sigma jk with respect to xk plus, I don't know, bj is 0. So this is your mechanical problem. And you can also write your thermal problem, obviously. So your thermal problem would be a similar story, but now it's much easier. It's just derivative of Qi with respect to Xi plus, well, that C, that scalar value is 0. Sorry, C is not. So let's call it C maybe. And plus that C is 0. And what does that mean for you? That just simply means one equation, its derivative of Q x with respect to x plus derivative of Q y with respect to y plus derivative of Q z with respect to z is 0. Plus C. All right. So these are, let's say, the strong form or the governing equations in 3D. But as you know, the idea here is to also create a 2D version of it. Trying to make it stand out a little. So that's that. And then if you want a 2D version of it, and then again, from next lecture on, we only use 2D. So I'm going to change this 3 to 2. And all you have to do is to omit the third component. So I'm going to just kill this guy. So that would be now a 2D version of the heat flux equation. And then for the mechanical problem, you would do the same thing. So the third one goes away. And then this third derivative also here goes away. And I also notice this should be by, obviously. Okay, so how you see how everything simplifies if it is 2D. All right. Usually, if you want to talk about 2D, there is this discussion of, is it plane strain or plane stress? It doesn't matter for us too much or for you too much. It really boils down to, to that relationship where you connect strain and stress together. Okay, so you need to be consistent only then. But we usually talk about plane strain. Okay, so we assume the third dimension is fixed, so there is no strain in the third direction. It's like a plate that you fix on top and the bottom. But it doesn't matter in any sense or in any way. The finite element procedure, the question, everything is the same. Only when you use your constitutive assumption, you need to be careful which one you are using, because the meaning of the material parameters for plane strain and plane stress, they slightly differ from one another. Okay, but this is it. So this is the let's say our point of departure for the next lecture, and from next lecture on, we will start from this strong form, and then we do exactly the same thing as we did before. Remember, the map that we have is still the same map. So now we know the strong form. What we want to do next is to derive the weak form and so on. Okay, so that's what we will do from the next lecture. Do you have any question? All right, then if that's not the case, thank you very much for your attention and have a good day, have a good weekend. Bye-bye.